next we're going to discuss the definite integral. And the definite integral is going to formalize the exact area we found using our approximations. Now, before even talking about the definite integral, we already discussed the indefinite integral. And the indefinite integral, remember, gave us a family of antiderivatives. So let's keep that in mind. The definite integral, definition, let f be continuous on a to b. The definite integral of f of x on a to b, denoted the same notation as the indefinite integral, except we're looking at an interval a to b, so we're going to put a at the bottom of the integral sign and b at the top. The definite integral is defined to be the limit of our approximation as the number of rectangles goes to infinity. And by that theorem, we could use the left approximation or the right-hand approximation. So right here, this definite integral is defined to give us the area. The indefinite integral is defined to give us an antiderivative. Those two concepts are not necessarily related, so you might be wondering why we're using very similar language and notation for an area and something that gives an antiderivative. We'll see why in the next video. But for now, let's just discuss this area. And first, the examples we did in approximating were all functions above the x-axis. What would happen if they go below the x-axis? What would happen if you had a function, I don't know, like this? Like that. And you wanted to, and I just said, ignoring everything we know about definite integral right now, which is not much. Let's say I ask you to approximate the area between A and B using rectangles. Well, you'd do the same thing. You'd divide it up into pieces, and you'd have areas of rectangles. But the one side of the rectangle is given by the function evaluated at a point. And if that's above the x-axis, that is positive. If it's below the x-axis, maybe I'll draw it on this one. If it's below the x-axis, and you just did the one side times the function evaluated at the point, you'd get the one side, which is positive, times a negative, because it's below the x-axis. And the formal definition of the definite integral will treat these areas under the x-axis as negatives because the function evaluates to a negative below that, below the x-axis. Now what does all that mean? Well, it means what we have here in this remark. Remark, let A1 be the area between f of x and the x-axis that lies above the x-axis. Let A2 be the area between f of x and the x-axis that lies above the x-axis, or below the x-axis. Did I say below for the first one? A1 is the one above the x-axis. A2 is below the x-axis. Well, the integral on a to b, or the definite integral of f of x on a to b would treat what's above the x-axis as a positive, because the function is positive up there. But it would treat what's below the x-axis as negative, because our approximation would treat them as negatives, because the function evaluates to a negative below the x-axis. So the definite integral is given by the area above the x-axis minus the area below the x-axis. And just so we have this concept, which we'll need for our last remarks on the net change theorem, the total area we'll define to be A1 plus A2. So let's look at an example. We'll look at two examples using that before discussing some definite integral properties. So let's give a graph. Let's do a longer graph. So on this one, I'm just going to draw a random function, and I'm going to give you the areas. For the next one, we're going to have to find the areas. Let's mark off some x values. Let's say this is -1. Let's say this is 2. Let's say that's 5. Let's say that's 10. No, 9. That's only one digit. And let's give you the areas. This one will be area. What numbers have we used? This right here will be area 3. That will have, by definition, area 3. This will be f of x. This down here, we'll say has area 4. This up here, we'll say has area 7. And given this setup, let's evaluate integral from -1 to 2 of f of x dx. Let's evaluate integral from, I might not have space here. We're going to do 3 of these, and then we're going to find the total area. Actually, I'll have space here. Integral from 2 to 5 of f of x dx. Integral from -1 to 9 of f of x dx. And then let's just say and the total area between f of x and the x-axis is, and then we'll fill in that blank. So let's do these 3 integrals given this setup, and then we'll find the total area. Well, if you're not given these areas, and you're not given convenient shapes, as in the next example, to find this definite integral, you'd have to go through the limit computation, which was attached to the previous video. Well, attached at the end of the previous video as a PDF with an email description. But here we have the areas, so we can find these integrals. Integral from -1 to 2. Well, here's -1, here's 2. The only thing there is a piece with area 3 above the x-axis. And this remark tells us that the definite integral treats that as a positive. So that's 3. Next, 2 to 5. This is read the integral from 2 to 5 of f of x with respect to x, or f of x dx. From 2 to 5. Well, what happens between 2 and 5? Well, we have that piece with area 4. But it's below the x-axis. The definite integral treats what's below the x-axis as a negative. So the integral from 2 to 5 there is -4. How about this next one? 1 to 9, or -1 to 9. Oh, I need that. -1 to 9. Well, area above the x-axis is positive. Area below the x-axis is negative. So here from -1 to 9, we're starting here. We're ending there. Areas above the x-axis are positive. So what's above the x-axis? A 3. What's above the x-axis? A 7. Areas below the x-axis are negative. What's below the x-axis? A 4. So we have 3 and 7, and a -4, which makes 6. And the total area is just all of those numbers added together, treating this as a positive. Total area is different from the definite integral, unless it's always positive. So the total area would be 3 plus 7 plus 4, which is 14. Let's look at another example where the areas are not given. Now, in this example, we have our function. The areas aren't given, but we are still going to compute 2 definite integrals, from 4 to 6 and from -4 to 9. Now, to find these areas, you don't have to worry about equations for any of these lines or anything, because notice what we can do. We can break down all of these sub-areas into triangles and rectangles. And you could also have like a circle, or well, I guess it wouldn't be a function of a circle, so you could have like a half circle, depending on the example. But what we're going to do is find the areas of all of these rectangles and triangles, and then we're just going to add a bunch of areas up. So first, well, notice these are all right triangles. And for triangles, what's the formula? Half base times height. But for a right triangle, the base and the height are given by the legs. So it's half leg times leg. So here we have a length 1, and here we have a length 2. 1 times 2 is 2. Half of 2 is 1. So I'm going to fill in the areas like this. Now for this next long rectangle, this right here is a board division. You could do it as this rectangle over here plus this rectangle. I'm just going to treat it as one rectangle. I'm just going to get rid of that y-axis piece. What is the height of this rectangle? Well, it's 2. What is the other side? Well, the other side goes from negative 3 to 4. So it's 2 by 7. So 14. How about this triangle? Well, the height is 2, the other side is 1. So again, we have a 1. What about this rectangle? The one side is 1, because it's 5 to the 6. The other side is 3. So we have 3 times 1 times a half. So that's 3 halves. And how about this last rectangle? Well, it's 3 by 3, which is 9. So that's actually a square. So we have all these areas. Now we just have to interpret them properly using that previous remark. What's above the x-axis is positive. What's below is negative as far as the definite integral is concerned. So first from 4 to 6. Well, 4 to 6 is this interval. What's above is positive. What's below is negative. So 1 minus 3 halves, negative 1 half. And how about this last one, from negative 4 to 9? Well, that's the entire thing. So what's above the x-axis is positive. What's below the x-axis is negative. So now I have to add all these numbers. So what is it? 16 minus 9 minus 3 halves. So what, 5 1/2? So the definite integral treats what's above the x-axis as a positive area and what's below the x-axis as negative. Now, just like the indefinite integral, we're going to have some properties of the definite integral. And proofs of these properties are largely based on area interpretations, and I'll discuss a couple as we go through them. We have 5 properties of the definite integral. First, the integral from a to a, that's incorrect, it should say f of x dx. From a to a. Well, what does that mean from a to a? Well, from a to a will just look like that. Area of a line would be 0. But more specifically, remember the definite integral is defined by doing an approximation using rectangles and then letting the number of rectangles go to infinity. So here, if you tried to break this into rectangles, well, you can't do it because each rectangle would have side length 0, would have base length 0. So if you're trying to find that area, well, that area would be 0. So integral from a to a is 0. How about the next one? From a to b, integral from a to b is negative integral from b to a of f of x dx. So if you flip the bounds around, the cost there is a negative. And we'll see that in the next video. We'll see that. 3. Integral from a to b of f plus g or minus g is the integral of f plus or minus the integral of g. Just like with limits, just like with derivatives, just like with indefinite integrals. If you have a bunch of things added together, you can do them one at a time. And that's because it follows from the limit, but more specifically, it follows from finding the areas of the rectangles. If you have f plus g, you can break the rectangle into an f part and a g part. or you could do them together as f plus g. 4. Integral of a constant times a function is the constant times the integral. Just like with limits, derivatives, and indefinite integrals, if there's a constant in front, you can pull it out and then do your computation. Very convenient. And 5, integral from a to b is integral from a to c plus integral from c to b, where c is between a and b. Remember, this means in. So c is in the interval a to b, not a and not b. I mean, I guess it could include a or b. But what does this even mean? Well, we'll use this in the next video. But what actually does this mean? Well, if you want, for example, the integral in the previous one from 4 to 6, well, you could do that by first doing the integral from 4 to 5, and then adding the integral from 5 to 6. So I like to see this fifth one as kind of, if you want this area, well, you can chop it into 2 pieces and find this area, and then find this area and add them together. So these properties, we'll use these properties, especially in the next 2 videos. We'll use all of these properties at some point in the next 2 videos.